Okay, so here's video 2, the rest of our notes. Complex roots. So there's a whole entire numbering system, right? That's its own infinity known as complex roots. Okay? Now, my story is, and it's a fake story, I made it up, but in the 1400s, 1500s, 1300s, when mathematicians were just getting around, they were all men. Okay? And as we all know, men need answers to everything. Okay? So, they came up with this question. They were like, okay, x squared plus 1, right? This was a problem.
Can you please stop?
This was a problem. What happens when you solve this equation? That's definitely an equation. Everybody agreed. They were like, what's the solution to this? Well, if you solve it, we would subtract 1 from both sides, and then you take the square root. And they had a problem with this, right? Your calculator can't do that.
Why?
Because your calculator is programmed to do real life things, right? But those guys in the room needed to have an answer, right? And they're fairly creative people, and creative people have something called an imagination.
Oh, I got that.
So they could imagine that there was a solution to this, right? So they came up with it. They made one, right? They made one. And everyone's like, oh yeah, that makes perfectly good sense. And they all agreed that the square root of -1, they're going to call I. I for imaginary number. Because there's not a solution, but we can imagine that there is. Because over here on the graph, a solution is where the graph crosses the x-axis. Does this graph cross the x-axis? No. The graph does not cross the x-axis. So there's no real solution. No real solution, right? These are all the real numbers here on the x-axis. So there's an imaginary solution. Okay, we call these complex numbers. And it comes in a form, there's the real part and there's the imaginary part. Okay, so all imaginary numbers come in pairs. There's always a pair. Okay, if a plus bi is a root, then so is this other one. Okay, it's a minus bi. They come in pairs. One of them is the positive pair, and the other one is the janky negative pair. But they always come in pairs. And the only thing that changes is the sign between your real number and your imaginary number. Okay, and these are called conjugates. Okay, these are called conjugates.
What are conjugates?
These two pairs of imaginary roots. Okay? The pairs of imaginary roots are called conjugates. You can't have one without the other. They always come in pairs. Okay? So what is the conjugate of positive 4i? Well, it's negative 4i. If one is positive, then the other one is negative.
Oh, really?
Right? You have supporters of one side and you have detractors from the same side. Right? There's always a pro and a con to just about everything. So there's a positive and a negative to all these conjugates. So what is the conjugate of negative I?
I.
It's positive I. Well done. Positive, right? They're always the same thing with a different sign. One's negative, one's positive.
Is it fine if we put a plus sign next to it?
Yes, you can put a plus in front of the I. You won't see that on a test or anything, but you can do that if it reminds yourself. Okay, 2 minus 3i has a conjugate of 2 plus 3i. The only thing that changes from your conjugate is the minus becomes a plus. Nothing else changes from your conjugate except for those two parts.
Yeah, I think I know this one.
Negative 4 plus 2i has a conjugate of?
Negative 4 minus 2i.
Minus 2i. In unison. Brilliant, right? That's what a conjugate is. All of these complex numbers always have a conjugate.
Get the hell out.
Okay? They always have a conjugate pair. They always come in pairs. Okay, did you know that there was a fundamental theorem of algebra? Well, there is. It just says that every polynomial can be written as a multipliers of factors, right? This is everything can be factored. That's exactly what the fundamental theorem of algebra is saying. Everything can be factored. So here we have a graph to the shown. We know that x equals I roots of 3 is a 0. I roots of 3 is a 0. What is the least possible value of n? N is the degree. So this is like, is it x to the 4th? Or is it x to the 5th? Or is it x to the 3rd? Right? What type of a function are we talking about here? Okay? So let's see. We know that every root has, at least a complex root comes in pairs. So it's at least an x squared. Okay, so your complex roots, that's going to say complex, is at least an x squared. Okay, in order to get I roots of 3, there also has to be negative I roots of 3. So there's 2 roots there, means we have an x squared somewhere. Okay, now let's come over here and see what else do we have from our graph. So here we have a graph that bounces, right? This is a bounce. So what's the multiplicity of a bounce? 2. So that's another x squared. Because we have a bounce, that means that we have another x squared, part of our function here. And what is our graph doing here? Right? It's crossing normally. So what is the multiplicity of something that crosses normally? X to the 1st. Right? So we can create, right, a polynomial which would have x squared from the complex roots. It would have x squared from our multiplicity there, our bouncing, and it would have an x from our crossing, right, the graphical behavior at the x-axis. So we are always multiplying these things together. So this should be at least an x to the 5th power equation. X to the 5th power. We just have to add up your powers. So 2 plus 2 plus 1 is x to the 5th. Right? Plus dot, dot, dot. There might be an x to the 4th or x cubed. It might have all the things, but we're not going to do that just yet. So this is going to be at least a 5th degree polynomial. We have 2 zeros from our complex value. We have 2 from our bouncing, right, our multiplicity. If the graph bounces at the x-axis, it has a multiplicity of 2. And then we have 1x from where it crosses as a multiplicity of 1. Okay? Pretty good. Okay, inequalities, let's see. F of x, we are referring to the y value. When we say f of x, that's the y value. Okay, so if f of x is greater than 0, right, that's what this means. The y values are greater than 0, greater than 0. Y values greater than 0. That's what this reads. If the y values are greater than 0, that means the graph of x is above the x-axis, right? Because that's where our y values are positive. And if f of x is less than 0, then the y values are below the x-axis. So f of x means y values. Where's your y value below your x-axis? That's what this means. Okay, so let's try and solve some nonlinear inequalities. Okay. Create a sign chart. That's going to be kind of neat. That's pretty easy. Test values. We're not going to do this, whether they're positive or negative. Okay, we're going to use our n behaviors and what we know about multiplicity. Okay, we're going to use our n behaviors and multiplicity in order to do our solving, our solution. Okay, because your solutions are intervals. They're intervals. Okay, your solutions are an interval where something is happening. Right? We have an x1 term and we have an x2 term. Intervals are always x values. Intervals of increasing and decreasing, intervals of concave up and concave down, intervals of constant, right? We've talked about intervals before. So we want to do three things. We want to figure out what the zeros are, our solutions. Okay, so that comes from each of our factors. X minus 3 has what as its solution? Right, positive 3, because positive 3 minus, what we're doing is we're setting each of these equal to 0. So x minus 3 equals 0 means x equals 3. Okay, x plus 1 equals 0, so x equals negative 1. X plus 4 equals 0, so x equals negative 4. Okay, so those are your zeros. Right, that's where the y values equals 0. That's our first part, x equals these numbers. Okay, so let's put them on a number line, right? So we're going to do what's called a sign chart. This is called a sign chart. We're just figuring out where is it positive and where is it negative. Okay, so let's put our values on here. Negative 4 is the farthest left. Negative 1 is the next farthest left. Positive 3 is the greatest of our three zeros. So we put it on a number line. So we need to figure out where, if our y values are positive or negative on each of these intervals. Okay, so we have everything to the left of negative 4. We have the stuff in between negative 4 and positive 1. We have the stuff in between 1 and 3. And we have the stuff to the right of positive 3, right? So we have 4 intervals that we are checking here. 4 intervals. So let's do this. So let's talk about our graphical solution here. Okay? If I look at my x's, x times x times x, this is an x cubed equation. Okay? So think about the graph of x cubed. It has a negative infinity on the left, and then it swoops in and does like this, and then it goes off to positive infinity on the right. All positive cubics look like that. So if we apply that to our graph here, we're going to come up through negative 4, go back down at positive 1, right, because it's all multiplicities of 1, and then come back up after positive 3. Okay? This is what the graph of our cubic is going to look like. X times x means it's a cubic equation. So look at our intervals. To the left of negative 1, to the left of negative 4, our y values are all negative. The y values are less than 0. Okay? What's happening in between negative 4 and positive 1? It's above 0. The y values are positive between negative 4 and negative 1. What's happening between negative 1 and positive 3? They're below 0 again. Y is less than 0. And then to the right of positive 3, they're positive. Y is greater than 0. So let's take about this and look at the intervals. Where is f of x greater than 0, right? Where is our y value above the x-axis? What were those intervals? From negative 4 to negative 1. So negative 4, that's negative 4 to negative 1, right? That's one interval where our graph is above the y-axis. Above. And the other one is from 3 to forever, right? 3 to infinity. Those are the two intervals where my graph is above the x-axis. And then where was it below the x-axis? Right. So negative infinity to negative 4, right? All the way. And then again from negative 1 to 3. Okay? So this graph has two intervals where the graph is above the x-axis and two intervals where it's below the x-axis. Okay? And there's another example that we can do in a minute. Okay, so let's see. We have a negative 2 solution and a positive 5 solution. Okay? So because it has a multiplicity of 2, the graph is going to bounce at negative 2. So our standard cubic will hit negative 2 and then come back down. and then cross again at positive 5 because it has a multiplicity there. So we have two intervals of negative. We have less than -2, or equal. It is actually equal there, isn't it? So let's do this. Let's just erase that less than, right? Because it's still negative, and it's negative, and then it's negative all the way to 5. Okay, so all these places are where the graph is below or touching the x-axis. So we'll put a bracket on 5 because that's where it is another 0. Okay, and then where is it positive? Well, it just says where is it less than 0. So that's our only solution. From negative infinity to positive 5, that's where a graph is below the x-axis. Okay, so you find your zeros and then what you know about our graph in order to do the other stuff. All right, we'll talk more about that later. Okay, bye.